who here has used Vagrant? Raise your hand. OK. Who here has heard of Terraform? Raise your hand. OK. Who here is using Terraform to provision their production environment? OK. That's going to go up after our speaker comes up here. Armon Dadgar is the co-founder and CTO of HashiCorp. The company has brought to you some of the most amazing DevOps tools that you're using every day to handle infrastructure challenges far and wide. They're still doing some really great stuff, and Armon has worked at a series of awesome companies and co-founded some great things. We're really happy to have him here as our keynote speaker. Let's give a round of applause for Armon.
Thank you. Good morning, everybody, and thanks to Mario for organizing and the overly kind introduction. So today what I wanted to talk about was service mesh for microservices, right? And I know that sounds like a ton of buzzwords colliding with other buzzwords, so we're going to sort of decompose that and ease into it so it's not just going to be jargon the whole time throughout. You guys got a super brief intro. My name's Armon Dadgar. I'm one of the founders and CTO of HashiCorp. You'll find me all around the internet as just Armon. I plan to post copies of the slides afterward to Twitter, so you'll find them there. And if you have any follow-up questions, please feel free to reach out and follow up with me online or offline after the talk. So based on the show of hands, I'm going to guess there's sort of a reasonable familiarity with some of the tools that HashiCorp makes. But I thought it might be helpful for folks that don't know kind of the full breadth or aren't sort of as aware of things outside of maybe Vagrant or Terraform to just talk quickly about kind of our mission, our scope, what we think about. So for us, when we talk about kind of the HashiCorp goal, it's how do we deliver end applications, right? That's where the value is. Every other tool, including the ones we make, the sort of below that line, are plumbing, right? And that's kind of how we think about our tools, is we're here in support of delivering your applications. So in thinking about that problem, we think there's kind of 4 different layers to the problem. There's how do we provision the underlying infrastructure, whether low level, bare metal, whether virtualized, whether super high level platform as a service. And our big focus there is our Terraform tool. Then there's the challenge of how do we secure all this infrastructure. So we have all sorts of endpoints that we want to protect, things like databases, machines. We have cloud credentials. How do we store those things? How do we distribute them securely? How do we protect our data? And our focus there is with Vault. Then we have a challenge of how do we run our applications across multiple environments, right? On-prem, cloud. All of these have sort of different APIs, different operating environments, but we want to give our developers a consistent experience. And our focus there is Nomad, our application scheduler. And then the final piece where we'll spend more time today talking about is how do we connect and wire all these things together, right? How do we have our on-premise applications talking to our virtualized apps, talking to our containers across multiple environments? It's all about the network, right? And so that's the last piece of this is Consul and the service connectivity that binds all of these things together. So with that, before we jump straight headfirst into service meshes and microservices and all that kind of fun stuff, I thought it would be useful to start with, where are we today? Where is the kind of starting point for all of this stuff? So I think classically when we talk about the prevailing application architecture, what you have is the monolith, right? It's a single large application that we're delivering as sort of a single unit, but it might have many subsystems as part of it. Right? So the example I always like to use is assume this monolith is desktop banking. A might be our login portal, B might be check balance, C might be bill pay, D might be wire transfer. Right? So these are kind of discrete functions that are most likely being developed by independent teams. Right? The team that's doing the login portal probably different than the team that's doing bill pay. Right? But we're compiling it together and releasing it and delivering it as a single packaged application. We're compiling it to one giant jar, and that's the thing we deliver, right? And so what's nice about this system, right, there's few properties that are nice, and they're mostly operational, is how do these systems interact, right? How does subsystem A talk to subsystem B? And in practice, you mark that method as public, it exposes a function signature, and then subsystem A just calls that method, right? So it's an in-memory function lookup, we jump to that function, we execute it, and then we jump back to subsystem A. Right? So this is nice, it's easy, it's kind of built into the language itself. If we need to leave our system, right, what we're probably doing is talking to a data store, right? Because we've kind of compiled in all the business logic as part of the monolith. So the things that tend to live on the outside are data. And so in practice, what you see is a static IP, which is either taking us to a load balancer or a VIP or the database directly, but probably just hard coding a static IP to a database. Great. So now as we want to talk about scaling up our monolith, right? We might hit the limits of what one instance of it can serve. What do? Right? We can't scale the individual pieces separately. So we can't say we need more login capacity and less bill pay capacity because it's all packaged as one. So really the best we can do is stand up additional copies of the monolith itself and then put a load balancer in front of it, right? So we'll set up as many instances as we need, split the traffic across them, and that way we can sort of horizontally scale out load to the system. So the final challenge in this architecture becomes how do you secure it, right? And what you tend to see is sort of a zone-based architecture. On the left, I have my sort of internet-facing demilitarized zone, right? Traffic's coming in from the public internet, hitting my load balancers, and from there going to my app server. And what I'm probably doing is splitting that with a firewall to say only the load balancer can get to my app tier, right? And then I might have another tier which separates my application from the backend database, second set of firewalls and VLANs potentially to segregate my app zone from my data zone, right? This is kind of the classic approach to networking with the monolith. Okay, so what's changed, right? Like that seems great. Seems like we had good answers to all of the common problems. Like why do we need to rethink about this at all? I think the first kind of major transition we're going through is one of application architecture, right? We're shifting away from saying I want to deliver this monolithic application to I want to deliver these isolated units of functionality, these microservices, right? Sort of buzzword du jour, right? We used to call this service-oriented architecture. Now we've slapped micro in front of it, but functionally kind of the same idea, which is what's the discrete scope of functionality and deliver that as an independent application. And these things compose together with API calls and RPCs. They're talking over the network, right? So the advantage if we do this correctly is we get away from the lowest common denominator. And what I mean by that is in this monolithic world, if there's a bug in our login portal A, team A has to wait until B, C, and D are all ready to cut a release, right? So if team A says there's a bug in login portal, we want to turn around a build today, then they have to coordinate across all the other teams to say, is master in a place we can build? Or is the integration test passing? Can we actually compile and cut a release? And what you tend to see in practice is the monolithic release cycle is slow, right? It's weeks to months. So it's hard for these teams to run at different speeds. Versus if we can split this and say, you know what, all that matters is the API contract between us. As long as A is not changing its API contract and they're just fixing bugs, right? They can release 10 times a day, and B can release twice a year. And it doesn't really matter. We get this sort of decoupling, and they can run at different speeds. So this is great from a development efficiency perspective, because now we can sort of move as fast as our team wants to move, right? As long as we keep our APIs sort of compatible. So what's the trade-off, right? What's the caveat, right? Nothing in life is a free lunch. And so what we've gained in one hand in development efficiency, we're trading in sort of equal measure for operational challenge, right? So the first major challenge that we inherit is how does service A even discover and connect to service B, right? Before it was mark it as a public method, A just calls that method, and it's an in-memory function lookup. Now, B is not the same app, it's not on the same machine, it exists somewhere over the network. So A needs to somehow find out where is B running on the network and connect to it, right? The other challenge is there's probably not one copy of B. You're going to run multiple copies for availability, for HA, to scale out, whatever the reason might be. It's not going to be one copy. So how do we think about A needing to bridge that gap? It can't just hard code the IP of one instance of B. So historically, what you would see is put a load balancer in front of every service tier, right? A hard codes the IP of the load balancer, then our load balancer brings us back to service tier B, right? And I think the challenge with this is sort of threefold. One is the load balancers tend to be manually managed. So he said, great, I brought up a new instance of B, now I filed a ticket, and I wait 3 weeks until traffic hits that instance. So great, we got all this development efficiency, I can release 10 times a day, it just takes 3 weeks for any traffic to get to it. So, we're seeing this sort of trade-off between the operational cost of the system versus the sort of development cost of the system. The other side of this is when we talk about the load balancers, they have a true cost, right? There's both a financial cost, they're not free, we have to pay for the load balancers, but also a performance cost, right? Because it's not service A to service B on the network, it's A to load balancer to B to load balancer back to A. So we're taking our network distance and sort of doubling it between all of these services. And so that's kind of okay if it was just A to B, but in practice it's A to B to C to D to a database and back. So we're already taking sort of a function call that we would have measured in nanoseconds and turning it into a network call, which we're now measuring in milliseconds. So something like 6 orders of magnitude worse. And then we're taking that and doubling it by adding more things in the path. So there's already this performance penalty that we're paying that's pretty serious from going to this model. So how do we think about minimizing some of that? So a bunch of load balancer challenges. So that's just happening at an application architecture level. At the same time, we're kind of going through a seismic shift in terms of how we think about the infrastructure itself. So independent of application architecture, we're starting to adopt cloud environments, right? And these bring with them higher failure rates, sort of more ephemeral infrastructure. Instead of our VM living 6 months to 2 years, it might live 6 days to a few weeks, right? So we have a much higher rate of change that's putting pressure on how we traditionally think about our networking, but we also have higher rates of failure, right? So we need to be able to react to these things better. And then at the same time, we're bringing in containers as well, which take that same trend and multiply the problem by another factor, right? So even higher churn, even more ephemeral, right? So how do we start to think about this sort of highly dynamic infrastructure that's coming and going, we're scaling up and down, and sort of the mismatch from our traditional networking, which is much more static and slower. So all of that kind of brings us to the first challenge, the first topic, which is service discovery, right? Which is really how do these things find each other and route to one another, right? And I think what you find is sort of there's a common approach, right? Whether we're talking about using Zookeeper, etcd, Eureka, Consul, they're all fundamentally applying the sort of notion of a registry, right? So we have the central registry that has a bird's eye view of every service. When a service gets launched, deployed, whatnot, it gets populated and registered as part of the central registry. So we know about every service everywhere. And what this lets us do is then dynamically discover endpoints. So when service A comes up and wants to talk to B, it's not hard coding an IP, it's querying a registry and saying, I want to talk to B, where is B currently running? Right? How do I get to it? So what this lets A do is skip over a load balancer and connect directly. Right? And because we're not hard coding an IP of B, we can scale B up and down. If a particular instance of B fails, as long as A retries the connection, it'll connect to a different instance of B. So the registry gives us a way to sort of shield the dynamic nature of the infrastructure, right? We can mask the ephemeral nature of instances coming and going and use the registry as sort of an up-to-date what's running where and make sure we bind everyone correctly. The challenge that's sort of always been kind of an exercise left to reader is what happens if it's not your intended downstream, right? It's not A who's connecting to you. It's some random attacker or malicious service, right, that's on the network, right? So there was a 0-day vulnerability, attacker gets on box, and now they're connecting to a service saying, I'd love to get the credit card information for the users. Please send that over, right? So how do we deal with this? Historically, it's been you deal with it at the network layer, segment your network, use firewalls, use VLANs. Don't solve this at an application layer, right? So I think this brings us to sort of the topic of service segmentation, right? How have we traditionally thought about this problem, right? And so when we talk about segmentation, it might be the buzziest space of them all, right? You got micro-segmentation, nano-segmentation, pico and femto segmentation, you got it all, right? At the core of it, though, it's all a very simple idea, right? I have a shared physical network that I'd like to split into smaller logical segments. That's it, right? And we can call them micro, pico, nano, whatever you want, right? But the idea is shared physical sub-network, then we're splitting it into these smaller segments, right? And the segments could be of different sizes. There's many different technologies to do this sort of segmentation, right? The most sort of prevalent would be virtual LAN and firewall. Those are kind of the most common. But you'll get into software-defined networks, overlays, other sort of technologies to achieve this sort of similar segmentation, right? In practice, what we tend to see, though, is that these segments are still coarse-grained, right? If you look at a VLAN, right, you still have hundreds, if not thousands, of servers and applications running on that VLAN. So there's still a very large virtualized segment, right? And so this is a problem. So if we overlay that onto the monolithic architecture, what we see is we have sort of 3 zones, 3 segments, right? We had the DMZ zone right on the left, we have our application zone in the center, and we had sort of our database zone on the right, right? So this is kind of historically how we did it. But now if we overlay sort of this transition to microservices on top of that, the middle zone starts to get a lot more complicated, right? Because before our traffic was strictly sort of left to right, right? What I mean by that is it went from load balancer to the app. The app was sort of talking internally between the subsystem. It didn't really leave, right? And then it would talk right to the database. So it's sort of a single direction, right? Versus now there's this much more complex east-west traffic flow, right? As we get to the app tier, the services are talking among themselves, right? They're talking and consuming different APIs. So that inner zone has a much more complex communication path. So how do we now start to think about securing that? And you might look at that and say, it's not that complicated. Instead of 3 zones, why don't we just have like 6 zones and call it a day? But in practice, that's not what it looks like when you have a service-oriented architecture or a microservice architecture, right? It starts to look closer to this. This is really only 36 services, right? We work with customers that have 4,000 unique applications, right? And that would just implode Keynote's ability to even render the slide. So when you start to talk about these internal east-west networks, these paths are very complex. It's not obvious to look at this and say, where would I draw my firewalls and VLANs to segment this in a sensible way, right? And so when we talk about what we want to achieve, right, the sort of ideal is that the network segment is only as big as it absolutely needs to be, right? So if service A needs to talk to service B, we want a segment that's that size, right? And if C and D need to talk to each other, we want a segment only that big, right? The problem, and where things get messy, is in the real world, it's not clean, right? Because A also needs to talk to C, B also needs to talk to D. And so how do we deal with the fact that we can't just draw these clean boxes, right? And in practice, what you end up seeing happen is we'll zoom out and create a coarser grain network, right? We'll create a network that has A, B, C, and D, because now, great, we've solved the problem. Now we don't have these sort of inconvenient lines crossing the boundary, right? But inadvertently, we created the problem that we were trying to avoid, which is now if B is compromised, it can talk to C, even though there's really no reason those two should be able to talk to each other. It was just an artifact of us zooming out and creating a coarse grain network that we added this risk, right? So how do we sort of get around this problem? So that all lays the groundwork for me to now talk about Consul, right? So hopefully sort of demystify some of the buzz. So when we start to talk about sort of service mesh for microservices, what we're really talking about is saying, as we adopt that microservice architecture, right, that service-oriented architecture, what is that common wheel of problems that we need to solve, right? We need to solve discovery. The apps need to be able to find and route to each other somehow, right? We need to solve configuration. We've taken what used to be sort of a central config problem. We had our 10,000 line properties.xml file, and now we have 50 properties.xml files, right? We have properties.json, properties.yaml, properties.ini, and each of these 50 services has a separate config file. So we've gone from a central large config file to many distributed configuration files, right? So this makes it sort of a management challenge. And then the final problem is that segmentation challenge. As we go to these sort of service-oriented networks, how do we avoid having this large blast radius, right? These huge networks that sort of any point of compromise is sort of a major issue. So how do we start to secure all that? And so collectively solving sort of the problems related to a microservice sort of becomes a service mesh, right? So start to demystify. So for folks that are less familiar with Consul, it's actually one of our older tools, right? Predates, Terraform, Vault, many of the others. It was launched in 2014. It does a little over 1 million downloads a month. So it's actually our most broadly downloaded and used tool, right? Surprisingly. And we have individual customers who run north of 50,000 agents. We're working with one right now who has more than 35,000 agents in a single data center, which is sort of, broke many edge cases of the system, but they're now sort of up and running. And when we talk about sort of some of the public users of Consul, people who've shared their use case, you see there's kind of a whole gamut, right? You have people who are born in the cloud, super cloud native, sort of microservice first, organizations like Stripe, right? Very modern and sort of forward thinking. You have organizations that are literal clouds like DigitalOcean. And then you have the other end of the spectrum, extremely conservative private data center, born in a physical vault and paper ledger like UBS. And this affects all of them, right? And I think what's important is to recognize that these problems of discovery, segmentation, configuration are not unique to only sort of new school containerized applications. These problems exist anytime you have a network of services that need to talk to each other, right? We have the same set of problems across those generations of infrastructure, right? So as we start talking about kind of the first problem, that service registry problem, what we're trying to do is solve the problem of discovery. How do we have all these discrete services find each other, route to each other, and do it in a way that kind of masks the ephemeral nature of the infrastructure, right? And so what Consul does is act as a registry of all the nodes that are running, all of the services that are running on those nodes, and then what's the health status of all of that. So there's a sort of domain model of a node provides one or more services, and there's health checks associated with either a service or a node, right? You might say, it seems like an overly complex domain model. Why not just have a flat set of services, right? The reason for that is you want to map to the physical reality that maybe I have a service that's returning 200 OK. My service is healthy, but it's running on a node that's at 100% CPU utilization, right? So the node is actually in sort of a critical degraded state. So even though that service might be healthy, the node it's running on is not, and you don't want to route traffic to it, right? So having that sort of two-level model lets us capture that, hey, if the node that we're running on is not in a good place, it doesn't matter that the service is healthy. We still don't want to route to it, right? And vice versa, right? Maybe the node is good, but the service is in a bad place, and you don't want to route to it. So you want to have that sort of integrated view of both the node and the service. So once you have all of this information centralized, we expose it to the application through kind of a few different interfaces. One is DNS, one is an HTTP API, and one's a web UI. So what's nice about the DNS interface is effectively every application speaks DNS already, right? It's the most broadly deployed service discovery protocol in the world, right? So what's nice is instead of hard coding an IP, we can hard code a DNS name, and then our DNS resolver can fill that in, right? So in this example, what we're doing is basically looking up the Redis service, right? So you'll see there's sort of a specially formatted DNS request. We're asking for redis.service.console. And what this lets us do is say anything in the .console top-level domain gets intercepted and processed by Consul, right? We don't want to send it to our normal resolver because this is not a public, it's not a .com that we can resolve, right? This belongs to Consul, right? .service is sort of a keyword. Consul has a few keywords it understands that sort of change how it's doing the discovery. But service is saying we're doing a service-level lookup. And then we're saying I want a service named Redis, right? So we're using the name of the service rather than its IP. And then what you see in green is Consul is filling in the IP, right? So we don't hard code where is Redis running. We hard code that my web app needs to talk to Redis, right? And now if this instance fails and gets brought up at a different IP, right, our app is shielded from that, right? That ephemeral nature of the service or the fact that a failure might occur is now sort of shielded. Versus if we'd hard code the IP, it dies and moves to a new IP. Now we have to redeploy our web application, right? Another way of sort of looking at the exact same data is through the RESTful API, right? So DNS is great for simple integrations where we don't want to modify the app, but the challenge is, what if we want to do something richer, right? We want to do client-side load balancing, we want blue-green, we want traffic weighting, we want more intelligent sort of load balancing. DNS is a very limited interface. We can't return a whole lot with it. So Consul has a rich RESTful interface that will return much more information, right? So this is a similar lookup for Redis, but now we're getting back, service tags, right? Is it blue? Is it green? What version is this thing running? We're getting port information. We get what node it's running on, associated health checks, so on and so forth. So what this lets us do is do much more intelligent load balancing with it, right? We can either use this to automatically update API gateways, update load balancers, or if the client side is doing intelligent load balancing, it can consume this directly. And then the kind of final interface for it is the web interface, right? So there's not the application consumer, but the sort of operator consumer, which is we want to debug an issue. Where do we start, right? We can log into this dashboard, and Consul has a bird's eye view of what's running where, what's its current health status, right? So we can log in and say something is wrong. Why is our whole web tier in a critical state? And use this to sort of drive our remediation. So that's kind of the service discovery use case. The other challenge we see is we've gone from this world of sort of a centralized configuration, right, where we had the properties.xml file that configured the whole monolith. And what was nice about that is if we changed sort of the flag in that file, all the subsystems had a logical view, right? If I say we're in maintenance mode, then all of the subsystems, right, login, check balance, bill pay, whatever, all believe we're in maintenance mode. But now we have this challenge of these are all distinct services with different configurations. So if I want to put desktop banking into maintenance mode, I have to update 20 different services to say, by the way, we're in maintenance mode, right? So this becomes sort of a complex coordination challenge because we've made it distributed, right? So how do we re-centralize the configuration? So our goal is the source of truth should not be the config files at the edge. The source of truth becomes sort of a key value store in the center, where we've configured things like, are we in maintenance mode? What's our connection pool size? How big is our cache? Things like that. We define all of it in the center, and then the files at the edge, the config files, are just pulling in the fragments of it that matter, right? So if the login portal needs to know, are we in maintenance mode? Great. It reads that from the central config store, but now when we change it centrally, we can push it out and propagate to the edge in real time, right? So this gets exposed as a hierarchical key value store, has a rich HTTP API, and we have this sort of edge triggering capability. So we can push out in real time when we change maintenance mode false to true. We can distribute it in real time. You don't have to poll every few minutes, right? You can kind of push right away. There's also other neat capabilities like distributed locking. So if we want to build highly available services, right, where I need to run one copy of this thing that's always running, right? What I want to really do is have an n+1 availability story. So great, I run my one that's actually doing it, but I run a second one that's sort of a standby that's waiting to take over if something fails, right? So that's sort of n+1 story. And historically, what we would have done is solve it at very much kind of a hardware level. Probably do something like layer 2 heartbeating, do a virtual IP that would flip over between the services. And so we used a very much a hardware network-centric approach to building sort of highly available services. Versus, as we go and talk about cloud infrastructure, there is no level 2 heartbeating and there is no VIP, right? So how do we sort of think about solving it in kind of a higher level? And what Consul does is give you a distributed locking implementation. So if service instance 1 grabs a lock, it's allowed to process as long as it's the lock holder. If Consul detects that node has failed or the service has failed, it'll release the lock and allow the other instance to grab it and start processing requests, right? And so this way we kind of move the availability and failover to kind of a software level thing and not a network level thing. So here's just a basic example of how we use the key value store, right? What you'll see is it's kind of a hierarchical folder structure. We're doing a put on a key, service web enable foo. So this might be a feature flag for that, writing value true, and then we're reading the same value back. So we read back what we put in, what we would expect. This is another view of the same thing. It's sort of using the web console to go in and administer it. So we might have a whole set of keys, right? The different feature flags, foo, bar, baz, right? Maintenance mode, things like that. So we can manage it all centrally, right? So now we don't have to worry about, is there 1, 10, 50 instances of web? We change it in one place and push it out to the edge. So that kind of talks about the kind of stuff we've focused on in Consul since 2014 has been really those two. It's been the service discovery and the service configuration, and it's been sort of exercise left to reader on how do you secure your networks. And I think what we've heard in talking to users and customers for the last few years is that that exercise is sort of doesn't have a lot of good answers, right? So that's when we started looking at Consul Connect and said, is there something better we can do to provide sort of an integrated solution to thinking about the segmentation problem? So when we talk about Consul Connect, there's sort of 3 major pillars to it, right? One is, what is the set of rules that we use to manage in terms of who can talk to who? And that's what we call the service access graph. The second part of it is, how do we distribute certificates and assign identity to applications? And the third part is, how do you actually enforce things in the data path, right? So all the rules in the world don't help us if we're not enforcing them. So let's sort of unpack each of these. The first one is, what is the set of rules that we use to manage who can talk to who, right? And historically, when we talk about this, it's IP to IP, right? It's firewall rules. We say IP1 can talk to IP2, IP3 can talk to IP4, right? And the challenge with an IP-based management approach is sort of a few different things, right? One challenge with them is they have no context, right? So great, we created IP1 can talk to IP2. 5 years later, we want to do an audit of that to say, should that rule exist? Who do you talk to, right? Who do you check that should IP1 still talk to IP2? Then neither of them might even exist at this point, right? And so what you see in practice is that organizations never delete firewall rules, right? You end up with millions of firewall rules because they're never deleted, because there's no context to be able to understand, can I delete it, right? So that's one problem. The other problem is they're a fundamentally scale-dependent unit, right? So when I go to my security team and say, hey, I'm launching this new web service, my web service should be able to talk to this database, they can do that, look at that and say, okay, yeah, no, it makes sense, you should be able to talk to the database. Okay, great. What's your web server's IP? What's the database's IP? We'll add a rule IP1 to IP2. Great. And now I say, well, now I want 10 new web servers. Great, that's 10 new firewall rules, right? And I want a new backup database. Great, 10 more firewall rules, right? So what you start to see is there's a scale dependence where there's the logical thing, which is my web server should talk to my database, but then there's the physical reality of like, it scales exponentially with the number of nodes, right? So there's a sort of mismatch that's kind of annoying. The other property that's frustrating is that because we're leaning on the physical IP, this thing breaks as we use things like auto-scaling, as we use things like schedulers that move nodes around, right? So great, the scheduler put us on IP1, then it decided to move us to IP4, right? And now the firewall rule is meaningless, right? So you have this sort of mismatch of the dynamic nature of infrastructure that we're moving towards and the sort of static nature of firewall rules, right? And so in our view, when we started looking at this, we said, well, what do you really want to manage? You really want to manage that logical rule, right? The one that says my web server can talk to my database. Because what's nice about that rule is it's scale independent. I don't care if you have 1, 10, 1,000 web servers. It's the same rule. Web server can talk to database, right? And it doesn't matter what IP the web server is running at, right? It could fail. Autoscaler brings it up at a different IP. So it's all the same, right? Because we're talking about the identity of the service, not the IP of the service. So when we talk about kind of the rules Consul lets you manage, it's this logical service to service. You say my source service, web, my destination service, database, and allow deny, right? And these rules can be managed in different ways, right? It could be CLI based, could be API, could be the UI, could be Terraform if you're doing an infrastructure as code approach. And so here's sort of what it looks like, right? Here we're creating a low precedence rule saying the web service to anything is denied, and then a higher precedence rule saying the web server to the database is allowed, right? In this case, the precedence is implicit because web to database is more specific, right? Web to anything is more of a sort of general rule, and so we match on the most specific rule first. Similarly, you could manage it through the UI. This might be more comfortable for firewall teams that are sort of used to that, so they can come in and use a UI to manage the same set of rules effectively. So cool, we've said we're going to manage our rule set at the sort of logical service-to-service level, right? Web server to database. The problem with that is at the network layer, that doesn't mean anything, right? What you see at the network layer is IP1 is talking to IP2. So how do we sort of bridge the gap between the fact that what we want to manage is identity, but what we have is IP, and these things don't cleanly translate between one another, right? So what we want to have is a strong assurance of, I know the identity on both sides of the wire, right? I don't really care how the packets got there. And in fact, there's probably VPNs, load balancers, NATs, things like that in the middle, right? So my network is either actively or passively trying to mess with me. And I'd like to have encryption of traffic between my services. And when you start to talk about those constraints and requirements, it looks very familiar. It looks like the public internet, right? When we talk about the public internet, when I go to bankofamerica.com, I don't care what IP is bankofamerica.com. I'm not asking, Comcast, hey, open up the firewall between my house and the bank, right? It's great. I don't care how the packets get there. All I care about is when they deliver sort of a certificate that says bankofamerica.com and we establish an encrypted channel, it can be whatever it wants in between me and the bank, right? And I don't care what IP I'm hitting at the bank. They probably have thousands. So the question becomes, how do you take this well understood approach, TLS, and shrink wrap it to something that's sort of suitable within the data center? And I think when you look at sort of certificate management, right, the biggest pain point is the certificate distribution, right? And I won't embarrass us with a show of hands, but I think what we've seen is sort of the average life cycle of a certificate, and sort of you can sort of say yes or no in your mind, is dramatically longer than the average tenure of an employee at a company, right? And I think there's a very good reason for that, which is I don't want to work here when that cert expires, right? Someone else's problem. And so it's like, you see this so often, you're like, why, right? There's got to be a good reason. And the good reason is that the distribution and rotation is painful, right? And so you're like, I'm doing that once, and then not my problem, right? And the CA, we're going to make that 30 years because that's definitely not my problem when that blows up, right? That's going to be a nightmare. So what we really focused on with Consul was not saying we're going to replace your signing authority, because almost everyone has one, right? Whether it's Vault, whether it's Venafi, whether it's an HSM, whether it's AD, there is a signing route for the PKI certificates. The challenge is, how do you generate the certificates? How do you sign them? How do you rotate them? How do you manage them through their whole life cycle? That seems to be the hard part. So that's what we focused on with Consul. So the moment an application gets scheduled, right? Let's say a web server, what we're going to do is generate a public-private key pair locally on that node for the web server. Then we'll generate a certificate signing request on the client and flow that to the Consul servers. The Consul servers will then inspect it to say, is this within the right bounds, right? Did you ask for a 10-year certificate, right? You're asking for a cert signed as a web server. Are you, in fact, a web server, right? Or are you just asking for a database certificate, right? So we'll sort of do the authorization around, should you have this cert? Does the cert look valid? Is the format correct? Things like that. And then if that all looks good, we'll forward it on to the signing authority, right? Vault or whatever system to be signed, and then we flow the signed certificate back down to the client. The key here is these certificates are not long-lived. We're not going to generate a CSR that's more than, call it 72 hours. Right? So it's not a 10-year cert that now we need to manage for a decade in case it leaks and we have to have a cert revocation story and all that stuff. They're short-lived, and we're constantly rotating. So it's sort of time over 36 hours in, the client will generate a new certificate signing request, reflow it up, get it re-signed, and then flip over to the new certificate. So we're sort of doing this hand-over-hand upgrade every 36 hours, right, and constantly going to a new updated certificate, right? The format of the certificate itself is largely X509. So the same certificate you'd get from bankofamerica.com, effectively the same format, right? The slight twist to it, for folks that are familiar with Spiffy, sort of a CNCF project to standardize the way we talk about identity. And what this lets us do is have kind of the next generation of network applications sort of speak a common language. So our API gateways can speak a common language as our service mesh, things like that, right? So we're kind of converging to the spec. It's a very, very minor sort of addition to X509. So we sort of add that. So as you adopt these kind of next-gen network tools, all of them will sort of play nice. The other sort of major pain point, right, in addition to the 10-year certificate, is the 30-year CA, right? And so in looking at this, we said, why is that so long? It's because its rotation is even more astronomically painful, that we're like, we should just be retired when it blows up, right? And so we looked at that and said, how do you get away from that? Because that's also a bad thing. You don't want a 30-year CA, right? And really it comes down to how do you get good at automating the rotation of it? And so Consul kind of brings this with it in addition to the leaf certificates. So at any time, we can hit Consul and say, please rotate the CA. And what we'll do is generate or sort of connect to the new root if you're providing the root, and generate this intermediate cross-sign certificate, right? So we'll have an intermediate that's signed by both old and new root, and any of our new certificates that we're issuing go out under this middle cross-signed intermediate. So clients that are still under the old root can continue to validate the cert. Clients that have already switched over to the new root can validate the cert, and we can sort of operate in both modes. But because Consul knows about all of the certificates that it's issuing and nothing is long-lived, right? We know once we're sort of done, once all of our clients have switched over to their new certificate, right? The one that's sort of cross-signed by the new CA, then we can switch over and just eliminate the intermediate and the old CA. We just move to a chain that's strictly our new CA, right? So it's really about getting good about this rotation so that it doesn't have to become a once in a 30-year exercise. How do we get to a point where we rotate our leaf every day and we rotate our root every year, right? Okay, so great. Now we have a central set of rules that we can manage, who can talk to who. We have certificates that we've distributed to the edge, but what we're not yet doing is enforcing any access, right? And so when it comes to enforcing access, there's really only kind of two answers, right? Either the app is aware or the app is unaware. Those are our two options, right? So if the app is unaware, right, we don't want to modify our application, there's too many apps to retool everything. What we really do is deploy a sidecar proxy. It's another agent running on the machine that is sort of doing this for us, right? It's shielding the app so we don't need to do any code modification, right? The trade-off here is there's a slight performance penalty, right? We have to jump through this intermediate proxy, but we retain operational flexibility. We don't retool our apps. Maybe we say in development environments, we are not using this. We don't secure the dev environment, but we secure production. And because the app is none the wiser, it doesn't really matter. So what this looks like is something like this, right? So on each sort of machine or pod or container, you have sort of a setup like this. You have the application, and then alongside of it is the Consul client and the proxy. And so when the app wants to talk out to another application, what it's really doing is talking to the local proxy. The proxy is doing the service discovery transparently, so it's figuring out where is Redis on the other side. It's doing TLS, right? So it's establishing that TLS connection between the proxies, and it's doing the authorization of should you be allowed to talk to the other side. If all that checks out, the proxy connects you to the app, and the apps are sort of transparently talking through these proxies, right? So they're sort of none the wiser that anything has happened. The proxies themselves in Consul are designed to be pluggable, right? So we ship a built-in one just to get you started out of the box. But if you want to use Envoy, HA proxy, write your own proxy, that's all fair game, right? It's designed to be pluggable. There's sort of a thin API that you really need to implement. And so the goal is, use whatever proxy makes sense for you, right? So if you want to use at level 7 sort of rich capabilities of Envoy, great. Integrate that, and we have sort of a native XDS implementation around the corner. So what does it look like to actually configure this, right? For people who have used Consul before, you'll sort of recognize the service registration blob. But the first line is where we're just declaring what's the name of the service, right? What should Consul sort of advertise to the network, right? The new block is that connect one. And the moment we add the connect block, Consul takes over generating the certificate, rotating it, fetching CAs, doing kind of all that. The cert lifecycle will start happening the moment we just say this app is going to use connect, right? And then what we're configuring is what are the ports that my app should talk to reach upstream. So here we're saying 1, 2, 3, 4 should connect me back to Redis. So the view that the application then has is I just talk to localhost 1, 2, 3, 4. The app just hard codes that, and to that, that's Redis, right? It doesn't really care where Redis is actually running. What's happening is when the app connects to that, the proxy is then responsible to figure out where on the network actually is Redis. Right? It might not be on the same machine, probably unlikely. It's probably not on 1.2.3.4 as a port. So it's going to figure out what's the IP and port somewhere over the network, establish the connection, secure it with TLS. And sort of a neat sort of fallout of this, but also kind of a challenge for our developers and operators, is how do we think about using sort of our local tools as we interact with these systems, right? So if I secure, let's say, my database with a system like Connect, but now I'm a DBA, I'm a developer, I'm an operator, I need to connect to it and do something, right? I don't want to be sort of in the sort of nightmare world of how do I generate a client certificate and sort of figure out how to get p-SQL to serve this certificate, right? Like that's going to be a nightmare. So instead, we sort of took an SSH-like approach. It's sort of, if you've ever used the reverse tunnel mode of SSH, this is very similar. And basically what we're doing is saying, set up a reverse tunnel between local port 8181 and the Postgres service, right? Much like SSH, you do sort of -d 8181, and we have that reverse tunnel. And then we use all of our normal tools, right? So if we're using p-SQL to connect to our Postgres database, we just point it to localhost 8181, and we're sort of shielded from the fact that the proxy is doing this sort of certificate generation, establishment, and kind of all the auth behind the scenes. So we don't break all of our existing tools and scripts and process, right? We just sort of use an SSH reverse tunnel type approach. So the other way we can solve this, right, if our app, one option, application unaware, use the proxy. The other way is native application integration, right? So what's neat as we talk about Connect, unlike sort of approaches like a software-defined network or an overlay, those are super, super complex, right, in terms of the protocol, in terms of the libraries you need to actually implement a virtual network, versus really effectively what Connect is some minor sort of fudging around with TLS, right? It's effectively standard TLS. So the SDK is just a thin wrapper around just doing TLS. Right? So the first thing you need to do when you accept the connection is establish mutual TLS. Right? Here's a CA, serve your certificate, validate that the chain is properly signed. And then you do a callback to Consul to say, I'm a database, a web server just connected to me. Yes or no, do I accept it? Right? If Consul says yes, you accept the connection, continue processing it like normal. If Consul says no, you close the connection, Consul fires off an audit trail, and you go about your business. Right? So there's not much you really have to do to get the native integration to work. The nice thing about going down this route is there's almost no performance overhead, right? Your app is just doing TLS, basically. So the performance overhead relative to TLS is 0, right? The challenge is it requires code modification, right? So we don't expect that this is the most common approach. But if we're doing it, here's an example of the Go SDK, right? The first 4 lines are setting up the client SDK. So we're declaring that this is my service, right? Sort of the name of it. And the only business logic change was where we're setting up our HTTP server, we're sourcing the TLS configuration from the SDK. Right? Instead of us providing it from a config file, we read it from Consul. And what Consul is doing is dynamically filling in, here's your public-private key, here's the set of CAs to trust, and anytime a connection comes in, it'll do a callback before it hands it back to the app to say, yes or no, should I accept this? Right? And so that effectively becomes the one-line business change. Other than that, once the connection has been accepted, we process our HTTP API just like normal, sort of business as usual. So kind of zooming out when we talk about Connect, there's these sort of 3 major pillars. Pillar 1 is the rules that we manage, right? That's the service access graph, and it's how do we move away from sort of millions of IP rules to a much fewer set of service-to-service rules, right? A logical unit rather than a physical unit of management. The other challenge is how do you actually impose identity at a network layer? Like, it doesn't exist at an IP layer, and it's about distribution of certificates. So how do we automate certificate distribution, CA rotation, right? The kind of painful lifecycle bits. And then the final bit of it is app integration, right? Where there's 2 stories, right? App aware, app unaware, right? And there's trade-offs between them. So we've talked a lot about sort of the, what it does, how we would solve this. We haven't really talked about what does the system look like, right? What is it like to operate this thing? So when we talk about Consul itself, it's a single binary, right? It's sort of everything is included. It's both the client, it's the server, it's its own state management. Everything is sort of in that single binary. And what you operate it as is sort of a client-server architecture. So you run 3 or 5 servers per data center, and then anywhere from 1 to 35,000 clients per data center, right? Anything more than 35,000, maybe give us a call before you go heads first, right? And out of the box, the system is multi-data center aware. So if I have multiple data centers, I can wire them together, and the system can federate across multiple data centers. So the servers themselves are the brains of the system, right? They have all of the state. They have the registry of what's running where, what's the current health status. They have all the key value configuration of the services. They have the access graph of who's allowed to talk to who, right? So they're highly stateful, and they're processing requests from clients, right? Internally, they perform a leader election, so they use an algorithm called Raft, a variant of Paxos, so that they'll pick one of the nodes as the leader. That one is serializing writes and replicating to the other nodes. All of the nodes are part of sort of servicing client reads, though. Right? And so if we lose the leader, they'll automatically elect a new leader and flip over. Right? So what we don't want to do is create this giant single point of failure in the middle of the network where if we lose one console node, our whole data center goes down. So the design of the system is designed around nodes are going to fail, whether clients or servers, and the system should gracefully handle it in an online way. So the clients we run sort of everywhere, right? So you run a client on sort of every node in the infrastructure, and they're connected back to the servers. And they're really dumb. They're effectively stateless, right? And the reason they exist is to provide sort of a dial tone to the application. Because otherwise, we create this sort of chicken and egg, right? If I'm a web app that wants to query Consul, well, what address is Consul running at, right? So to solve my service discovery problem, I have to solve a different service discovery problem. So instead, what the client does is provide this sort of local dial tone. The app always talks to the local host port of the client, and then the client is sort of transparently shielding where is the server running. The server could be running at any IP address, servers could be coming and going, but the client doesn't care. It always talks to the local host client. So it's forwarding. The other thing it lets us do is act as sort of a distributed cache. It lets the servers push a bunch of work out to the edge of the network, so your central servers don't sort of implode under load. Right? And we'll kind of see how that comes into play. So the first kind of big challenge is like, okay, well, great. Now I've just said my app talks to the client talks to the server. How does the client know where the server is, right? I've just sort of moved around my service discovery problem, right? And the way this works is in the background, Consul makes use of a gossip protocol, right? So we have a separate tool, if you've ever heard of it, sort of very niche, called Surf, which is just purely a gossip layer. And Consul embeds that to provide this sort of background awareness of the cluster, right? There's two key features we get out of it. One is cluster membership, and one is failure detection. So we'll talk about both quickly. So when we talk about cluster membership, it's that challenge of how do my clients know where my servers are running, especially since servers could fail, they might come and go, we might be scaling up and down, things like that. Right? And similarly, clients can come and go. And so what this happens is all of the nodes in this cluster are participating in this background gossip. Right? They're periodically sending little messages, UDP messages, between the nodes to keep them up to date. So when a new server joins the cluster, it talks to any existing node. An existing server, an existing client, doesn't matter. And what will happen is that node will recognize, hey, this new server just joined at whatever IP1, start broadcasting to the rest of the cluster. Right? So that node will pick 5 of its peers and broadcast and say, hey, by the way, the server just joined at IP1. Those 5 nodes will pick 5 other nodes and broadcast to them, by the way, the server just joined at IP1. And so you get this tree where at every node you're getting a 5-level sort of fan out. As you can imagine, you don't need very many levels before you get to thousands of nodes. Right? So even at sort of tens of thousands of nodes, we're able to sort of distribute in sub-second that a node has joined or left the cluster, right? Because you get this very efficient fan out of the gossip. Each node is not doing that much work, right? It's not that one node has to broadcast to 10,000. Each node only broadcasts to 5, right? 3, 5, it's sort of variable. So what this gives us is all the nodes now have this awareness of who's in the cluster, right? We can also pass along a little bit of metadata, right, like versioning information. So in the background, we pass around what protocol versions does the server support or the client support. And so what you see in practice is you have these clusters where ancient versions of the Consul client, right, from 4 or 5 years ago are talking to the latest version of the Consul servers because in the background, they can sort of negotiate the right protocols. Right? So you can have kind of Consul 0.1 talking to Consul 1.3, and they're sort of negotiating the protocol. So you don't have to do this atomic upgrade of 1,000 nodes to the new version. Right? They sort of figure it out on their own. The other big thing it gives us is failure detection. Right? And so when we talk about kind of most distributed systems, the way they handle failure detection is through heartbeating. Right? So if we talk about a system like Zookeeper, for example, or Eureka, what you do is as a node, I come up, I register, and then I say every 10 seconds, I'm going to check in with you. Right? I'm going to check in and say, I'm still alive. I'm still alive. Right? That's a heartbeat. I'm basically heartbeating that I'm still here. Right? And the challenge you start to have is if I have a central set of servers, but sort of a distributed set of clients, my load becomes linear. Right? And there's like limits to how much I can vertically scale it. So if I have 100 nodes checking in every second, great, I have to do 100 requests a second. At 1,000 nodes, I have to do 1,000 requests a second. At 10,000 nodes, I'm doing 10,000 requests per second of background radiation. I'm not servicing real work. It's not asking for any useful information. I'm doing 10,000 requests a second of just I'm alive, right? And your servers are basically on fire just trying to keep up with this. So your trade-offs start to become, if I want a fast failure detector, right, I want to quickly detect a machine has failed, I need a short heartbeat interval, but that means my load becomes astronomical, right? Doing nothing means I'm doing 10,000 requests per second at idle, right? And that's difficult to scale to, right? Versus if I want a very slow failure detector, every 30 seconds they'll check in, and now I can say I'm doing a reasonable, 500 requests per second, right? But it takes me a long time to detect a failure and route around it. So you have this sort of uncomfortable trade-off. What the gossip layer lets us do is push all this work out of the servers, right? So every node, every second, picks another random node and pings it and says, are you still alive, right? 99.9% of the time, it'll respond back and say, yep, still here, great. If it doesn't respond, we pick a few peers, ping them, and say, hey, can you check if that node is dead? We think it's not alive, right? And if none of those nodes can reach contact, then we're reasonably confident. We've made several attempts to get to that node. It's probably dead, right? And so at that point, we can start broadcasting to the cluster, we think this node is down, right? And again, using that efficient sort of pick 5 nodes broadcast, it's efficient for us to broadcast to a huge cluster that we think a node has died, right? And so what this lets us do is get failure detection without any central work on the servers, right? We've pushed this work out to every node in the cluster. Every node only health checks one other node every second, right? So whether there's 10 nodes or 10,000 nodes, you check one other node. So the amount of work is sort of constant regardless of the cluster size. So what you see is even on enormous clusters of thousands and thousands of nodes, the servers are idle, right? Because they're not processing this immense amount of background heart beating constantly, right? We've sort of distributed that work to the whole cluster. So this is why the clients play this sort of important role in making the system scalable. So as we zoom out and look at kind of the data center level, what you have is something like this. You have your currently active leader, and a set of server followers that are actively being replicated to. And between them, you have RPC traffic and data that's being replicated. They're sort of sending traffic back and forth. And then you have your clients. They're participating in gossip alongside with the servers. And then they're making RPCs. So anytime a client wants to say, where's Redis running, it makes an RPC call to one of the servers to say, hey, query the registry, tell me where Redis is running, right? Because the clients are stateless. As we zoom out to sort of a multi-data center view, you see kind of a carbon copy of it. Each data center looks the same. It has an independent set of servers, an independent set of clients, and the only things that crosstalk are the servers themselves. So clients don't crosstalk across the data center. We don't want to create this sort of enormous amount of WAN traffic, right? If a client in data center 1 wants to query about something in data center 2, talks to its local server, that server queries the server in data center 2 and then forwards the response back. So you get a sort of multi-hop routing taking place. So as we talk about kind of Consul's role in the data center, it's really a control plane, right? Consul's goal is to provide that metadata of what are all the nodes, health status, configuration, routing information, who can talk to who, but it's not to sit in the data path itself, right? Data should not flow over Consul, right? We don't want it to become sort of a bottleneck where data is flowing back to a centralized service. And so I think where you see it most clearly is in this diagram of the data flow, where what Consul is doing is it's providing configuration information to the client in a sort of sidecar approach, or if the application is natively integrated, it's providing control information to the client, but the data is not flowing over Consul. The data flows proxy to proxy, or app to proxy, or app to app, right? The data path is not including Consul, right? And that's super important for scalability reasons. So as we talk about Consul in a containerized world or a Kubernetes world, the goal is to run the agent at sort of the largest unit of granularity available to you, right? And what I mean by that is, if you're running on bare metal, run a VM per machine, right? If you're running at a VM level, agent per VM. If the only unit you have access to is a pod, run it per pod, right? And the reason for that is not that it doesn't work if you run it sort of at a agent per container level. It's that you're doing a bunch of redundant work, right? Is that the node is sort of health checking, is my node alive? If I have 10 apps on the same node, I'm sort of 10x checking if that node is alive, right? It's sort of a bunch of wasted effort. So it's not that it doesn't work, it's just that it kind of wastes a bunch of resources, right? So you might use something like a daemon set to run a copy of Consul on every node in the kube cluster, right? But then a proxy per container or pod. So the goal of sort of Consul's architecture is meant to be sort of batteries included. It's the client, it's the server, it has a proxy out of the box, everything is there. It's highly available and scalable, right? So whether you want to be able to tolerate the failure of one server, you can run 3. 5 servers, you can tolerate the failure of 2. Any number of sort of clients you might want, and to make the system pluggable to different data planes. So kind of in conclusion, wrapping this up, I think what we see is there's sort of a common set of challenges, right? As we talk about infrastructure, it's all in service of that app, right? And when we look at a microservices architecture, there's a common set of operational challenges, right? So our goal was, how do we not end up with a patchwork of solutions, right? One looking at load balancing, one looking at discovery, one looking at segmentation, but sort of have an integrated view of these are all related problems. They kind of fall out of the same architecture, right? And how do we sort of package that as one solution? And so that's really what Consul becomes, right? It's sort of a single service mesh solution looking at kind of those common wheel of problems, whether it's discovery, config, or segmentation. And that's all I had. Thank you guys so much, and welcome to DevOps Days Detroit.